Hello students, I hope that you are good, well and fine. So we are back with logarithmic differentiation. So far we have discussed theory until up till what exercise 5.3. Okay. Now we will be having some idea about what do we mean by logarithmic functions and its differentiation, how it is going to help us. Okay. So let's right jump to our first thing, which is the outline. In today's session, we will be seeing some definition of exponential function, features of exponential function, definition for logarithmic function, important some observation about logarithmic and some theorems, and then logarithmic differentiation. So let's see. Okay, so definition of exponential function. So with positive base, so first of all, in exponential functions, we want positive base. Positive base with the condition it must be strictly greater than 1. Okay, it must be strictly greater than 1. Okay, the function defined like this, y is equals to fx in terms of x, like this. The b we are calling it as base and power with x. Okay, as you can be base power x. Okay, this is what your exponential function. Simple. Okay. Okay, clear? So far so good. So this is the way we are first introducing our exponential function. Okay, formally. Now let's see to the next slide. Now we will see some observations, some feature, some studies, the conclusion of those studies. First of all is domain of the exponential function is whole R, as you can see, whole R, the set of all real numbers. Okay, the range of exponential function is the set of all positive real numbers, only all positive real numbers. This means open at 0, open interval 0 to infinity, that's it. Okay, open interval 0 to infinity. The domain is whole R, which is open interval minus infinity to infinity. Simple. Okay, let us move to the next slide. Now some more observations, some more features. The thing which is that the point, this point is 0 to 1, 0 comma 1, not to 1, 0 comma point, this point 0 comma 1, this position in the Cartesian plane will be always there on the graph of exponential function, where we are taking our base as strictly greater than 1. Okay, this is a restatement of the fact that b exponent 0 is equals to always 1. You always know that. Okay, we know that any non-zero power 0 will give you 1. Okay. Okay, simple. Okay, now fourth says, so I hope that this third point is very clear to you, that this point will always be on the graph of this exponent function b power x. Okay, now fourth point says that exponential function is ever increasing. This means if you try to move towards the positive x-axis, towards the infinity, positive infinity, you will see the growth in the graph of exponential function. That graph always rises above, tends to what? The infinity, towards the y-axis infinity. Okay, so this means if you move left to right on the x-axis, the graph will rise above. Okay, clear? Okay, now fifth point. Fifth point says that for very large negative value of x, for very large negative value of x, for example, if you take minus of 10 to the power 10, so this is very large negative value, minus 10 to the power 10. Yes, the exponential function will be very, very close to 0. In other words, if you try to see, so the fourth point, if you connect these two things, not connect, if you find out the analogy, is that in fourth point we are saying if you move to the right side of the plus, if you move towards the plus infinity, if you move towards the plus infinity or move left to right, then the graph will be ever increasing. Okay, this means it is reaching the plus infinity of the y-axis. Okay, now if you move, the fifth point is saying if you move right to left, if you move right to left or the negative infinity, if you move towards negative infinity or right to left, then your graph will be very, very near to the x-axis, very, very near to the x-axis. That's what it is written, very close to 0. The function will very close to 0 means by graph, if you try to look at it, the graph will be touching the y-axis part. Okay, as if you go towards minus infinity. This only happens when as you go towards minus infinity. Okay, in other words, in the second quadrant, if you try to see, the graph will be in the first and the second quadrant. That's it. If you try to draw it, the graph will be in the the whole graph of the exponential function with base greater than 1 will be what? Taking the second and the first quadrant. Okay, clear? And this part is saying, in other words, in the second quadrant the graph approaches x-axis but never meets it. Okay, it is trying to touch the x-axis but it will not. Okay, simple. I hope that these points are very clear to you. The 1, 2, 3, 4 and 5th problems, very important points also. Okay, let us move to next. Now, definition of logarithmic. Now we will come to the logarithmic thing. We so far saw the exponential thing, definition, exponential points. Now it's time to define our logarithmic function. So if b is positive with greater than 1, any real number, then we say logarithmic of a to base b is x is what? X if b x, this will be what? Your x, bx is equals to a. Okay, in other words, you will see what we are trying to say. So logarithmic of a, log of a base b means what? So this logarithmic mean in term of exponent is that b power x is equals to a in term of exponential. Okay, in terms of logarithmic we will say this, in terms of exponent we will make the sense like this thing. Okay, so what we are trying to say is that, okay, so now what is, so let me just give you, so this is this in terms of exponent. In other terms, so log of a with base b, okay, log of a with base b is equals to some x. This is what this statement is saying. This English words, these English words are trying to say mathematically is this, the mathematical expression for these will be this, log of a, as you can see, log of a, yes, log of a with base. In log we write base here, okay, in the subscript of log, okay, and which is what? X. So this is in terms of log, and this can be C as x in terms of exponent in this manner, which means that b power x means x, b power x is equals to x. Okay, both are same, both mean same but in the different context. Okay, simple. Okay, let us move to next. So there are some important points about log. So obviously we are taking b, the base, as strictly greater than 1, but any real number. Okay, so we cannot make meaningful definition of log with non-positive numbers. That means we are taking 0 in it. Non-positive numbers means every real number except positive real numbers. Okay, every real number except positive real numbers. In other words, here the numbers will be negative numbers and 0 also will be there. Hence the domain of log. So this means the domain of log we will be saying as R positive. We will be saying as R positive. This means open interval 0 to plus infinity. Open interval 0 to plus infinity. Okay. So this first point says about the domain of logarithmic function, whereas domain of exponent function is every real number. Okay, now let's talk about the range of domain. If you remember the range of exponent function, the range of exponent function is open interval 0 to plus infinity. The range of exponent I'm talking about. Now let's focus on the logarithmic function. So you must know the range and domain for both log and the exponent functions. So range will be the set of all real numbers. So here the range will be set of all real numbers. So what is happening is that the domain of exponent function is the range of logarithmic function, and the range of exponent function is the domain of log. If you try to observe that, you will find the reverse thing is happening. And eventually you will learn that logarithmic function is just nothing but the inverse of your exponent function. Okay, simple. Okay, so I hope that it is clear to you. Let us move to next slide. So other points, other features. So the point 1, 0, this point will be on the graph of log function. If you draw the graph of log function, if you try to use the calculators to graph the log function, or if you try to Google it, you will find out that in exponential function and in logarithmic function you will get this point always be there. Okay, simple. Okay, sorry, in log you will get this, and in exponent function you will have 0, 1. Okay, sorry for that. In exponent you will have this in exponent. Okay, in exponent. But in log the reverse thing is happening. As you can see, in log what is happening, this 1 is now here, this 0 is now here, as you can see. Okay, that's why I already told you this is a kind of, not a kind, it is actually the inverse of exponential function. Okay, clear? So you will find this point on the graph of log function every time. With base, obviously we are talking about in the context where base is greater than 1. Now fourth point says the log function is ever increasing. The same thing is happening here, ever increasing. The same thing was happening in the exponential function. Okay, so log function is ever increasing. This means if you move towards the plus infinity on the x-axis, the graph moves, or the graph rises above, or graph moves down to upward direction in the plus infinity direction of the y-axis. Okay, now the fifth point, if x is near to 0, okay, the value of log x can be made lesser than any real number. In other words, if you try to move near 0 on the x-axis or try to move towards the origin in the Cartesian plane, then the log function behaves what? Then it will decreases. The graph will move downwards to the minus infinity in the y-axis direction. Okay, in other words, the fourth quadrant, the graph approaches y-axis but never meets. Okay, but never meets. Simple? Okay. I hope that these points are very clear to you. Very simple points. Okay, if you try to graph these, if you try to remember from the graph of logarithmic functions and from the exponent function, if you Google it, if you use the Desmos tool, if you use the GeoGebra tool, okay, you will get what? That you will see the visual things. Okay, so please use them. Okay, and also play with them with different bases. Okay, so let's move to next. Now, is it true that x is always equals to e log x for all real values x? No. Why? As you can see, in log x, the domain is what? All real numbers, but non-negative. X must be this, or in other words, x must be this, or in other words, x must be this. This is the same things, but different types of notations. Okay. Here we are talking about all real number. This means x could be negative. Take x is equals to -1. So -1 is equals to e log -1. But log is not defined on negative, or log is only defined for these for this interval. Okay, these notations. So this will be not same. Okay, clear? Okay, simple. Okay, so not true for this. If you are saying is it true, so no, it is not true for all real number. It will be true. It will be true if you are talking about positive real numbers. It will be true for if you are talking about positive real number. And obviously what we are taking as this base as e, this base as e. Okay, so if you, okay, I hope that it is clear. Okay, let us move next. Now, the derivative of ex, we are saying the derivative of ex is ex. You will later on find out, or you will see the proof why we take this. For now, just use this as fact that derivative of ex is ex. Okay, this means derivative of d by dx, ex is equals to ex. Okay, simple. Okay, and derivative of log x will be 1 by x. You will see that also, how we are saying that derivative of log x is 1 by x. Okay, for now use these as facts. Okay, for now use these as facts. Let us move to next slide. Now here we have to differentiate them. So very simple. So differentiate it. You know the differentiation. Okay, so first of all, you know the differentiation of e of x. So you don't know the differentiation of e of minus x. So first of all, differentiate it. You will get -1. Now differentiate the whole thing, or the outer thing. We are saying that this will be now multiplied. Now ex will be x. The inside thing will be the same. So derivative will be minus of e minus x. So derivative, this will be minus of e minus x. That's it. For this, derivate the inside thing. So derivative of the inside, we just saw that it will be 1 by x. We have to use as a fact. Now multiply with the outer thing. Outer thing derivative will be sine, derivative will be cos, and the inside thing will be the same. The same thing we are using the chain rule, or the variation of the chain rule, but directly. Now the same thing will happen. Derivative of this, directly use this derivative. The derivative is ex, just ex. Now multiply with the outer derivative, which is cos inverse x, will be 1 minus 1 by root 1 minus x square. What is x square? Which is inside thing. Inside thing is ex whole square, means e power 2x. Now derivative. So derivative of this thing. So derivative of this thing means minus cos x. Now derivative of outside thing is e power the whatever the power. So e power, so it will be ex. So the derivative will be this thing. Okay. I hope that you got the idea how we got these answers by just using simple chain rule. Okay. What we are always trying to do, just trying to derivate the inside thing, most inside thing, and then multiply the derivative of the most outside thing. Okay, clear? Okay, now, so these are the answers. Please do verify them. Now let us move to the next slide, and then we will, after this, we will end up our session. Okay. Okay, so in this part, we will learn to differentiate certain special classes of function in terms of the what form, this form. If y is equals to written in this form, explicit form, which is y is equals to fx. Okay, so far so good. And this fx is further written in some, this is what, as you can see, this is a function of x, or the expression in terms of x. Here the power is also some expression of x. If you try to see the previous examples, you got nothing like that form. You just simply use the your chain rule by simply. But here, if you face such sort of form, then how you will approach it? This means if you find written like this, y is equals to x power s, then how will you find the derivative? Very simple. Just try to put log to the both side. So if you put log to the both side, then what you will get? Log x power x. You will use the properties of log, which is, this can be rewritten as x log x. Now derivative, it is implicit function, so this will be derivative of this will be 1 by y, and multiply. Whenever you have y expression, you always multiply with this thing, and this will be now product. So x log x plus this will happen, so this means just 1. So your derivative, or y prime, will be y multiply with log x plus 1. And what is your y? Y is x power x. So your derivative will be this, in this form. Okay, simple. So your derivative will be of in this form. I hope that it is clear to you how we are using this form and using the logarithmic theory to this form to reduce and to get our answer easily. Okay, simple. Okay, now, so that's it. We have to now end up our session here. As you know the enough theory about log, exponent, and now you will have some working idea of log, that how we are going to use it in differentiation, as one example you just saw. Okay, in upcoming sessions you will be seeing the examples, more examples, and the more theory and exercise related to the, especially related to the logarithmic differentiation. Okay, so for now we have to stop it here. So thank you all. We will be back with the more problems for this, so that you can have greater and the bigger idea how we are going to use our logarithmic differentiation in differentiations. Okay, and then how can we reduce our effort to get the answer quickly and efficiently the correct. So again, thank you.